Okay, so in section 1.3, we're going to be looking at arithmetic operations on sequences. If you've taken a topology course, you know we've been sampling the topology of the real line when it's really convenient for our purposes. In this case, we're just going to show the relationships between the arithmetic processes and the ordering on the real numbers. So we're going to be adding, subtracting, multiplying, dividing, sequences. So we'll start with two sequences that we are going to say are Cauchy. So say we have an and bn where they are both Cauchy. Right, so we're going to consider the sequence an plus bn, and we notice that the following sequence inequality holds. So here we have first term, or not the first term, but I'm just going to call it a term. I'm going to call it the term 1, and over here the term 2, not necessarily the first and second term of this sequence. But if I get those, so subtracting the first term minus the second term to see if they're Cauchy, this sequence is Cauchy, we see that it's equal to this over here. And by the triangle inequality, that's less than an minus am plus bn minus bm. And from here, well, from last lesson, you should already be seeing something. You should now be able to see how to prove that an plus bn, that sequence, is Cauchy. So we're going to prove this, but I'm not going to do it Cauchy. You can do that as an exercise. I'm going to do it instead just assuming they're both convergent. So if an converges to a and bn converges to b, then an plus bn converges to a plus b. So not only are we proving that they're going to converge when we add the two sequences together, but we also can assert what that limit will be, which is a plus b. Right, so how does a proof work? This one, fairly straightforward. We're going to have several proofs in this section. This one being one of the more simpler ones. So first we choose epsilon to be greater than 0, as we always do. So there's a positive integer n1, right, such that when little n is greater than or equal to that big N, we have that our difference between our sequence and our limit point is less than epsilon over 2. That's just, we're basically just saying, hey, an converges to a. Same thing over here. There's an integer n2, such that n greater than n2 implies that bn converges to b. That's all we're saying. And this n1, the reason we're using n1 and n2 is because maybe an minus a isn't less than epsilon over 2 until n is equal to 44, right? With bn minus b, maybe that isn't less than or equal to, less than epsilon over 2 until n is equal to 1 million. Right, so we can't use the same n. That's why we're using n sub 1 and n sub 2, different n's for the different sequences, because they may not be the same. Okay, so next we have that we're going to let n be the maximum of them two. Why? Because, for example, like this one I said was 44 and this one I said was a million. Well, a million certainly suffices because it's greater than 44, right? So a million here is going to be greater than 44. So we're just going to choose the max because, well, the max will suffice for the other one. Right, so then from here we go to say, okay, well, if n is greater than n, which again is our max as we defined it up here, if n is greater than n, we have that for n greater than n1, we have n is equal to greater than or equal to n1. So an definitely converges to a, and bn also converges to b, and they're both less than epsilon over 2 with that choice of n. Well, what does that tell us? Well, that gives us that if we were to take this sequence, an plus bn, and subtract what we're claiming is its limit point, well, we just can rearrange the terms, and not even rearrange them, but have them equal to, well, this what we have here, And here we can use a triangle inequality to say this is less than or equal to this sequence minus an minus a plus bn minus b. And we know these two, because of our choice of n, are both less than what? Epsilon over 2, right? And if they're both less than epsilon over 2, well, then they're less than epsilon, right? So what does that prove? That proves that an plus bn converges to a plus b. So it's a nice proof. This is for addition. It's going to get a bit more complicated. So now I pose a question. If an converges to a and bn converges to b, does an times bn converge to a times b? Well, some of these proofs seem like they're obvious once you see them and read them, but you wonder how they came up with. And what we do is we basically, as mathematicians, we're supposed to, or not supposed to, but what can help us is kind of start with the end result that we want and kind of see what we need to kind of modify and work backwards to make it work, to make the proof work. So here we have an times bn minus ab, right? So this is what should happen if an times bn, the sequences multiplied, do converge to a times b, right? And here, a little clever step here is adding 0 by subtracting an times b and then adding an plus b, right? We're adding 0. And the reason we want to do that is because now we can take out an an, factor out an an from both of these two terms, and we can factor out a b from both of these two terms. By the triangle inequality, this is less than or equal to the following. So now, question is, can we make this less than epsilon somehow? Well, we're going to have to look at each piece separately, right? So we can definitely make an minus a since it's converging. We can make this as small as we want, right? So I'm just going to put, we can make this small. Same thing with this one, right? We're assuming they're converging, so we, okay. So both of these are converging. So we can make them arbitrarily small, right? So we can make this here and this over here small. What about b? Well, b is just a constant. So that poses no problem because if it's multiplied by this over here, well, it's just going to get small as well, right? Constant. So no problem. No problem making that small. Because the reason we're making this small is because we want this here to be less than epsilon. But now what about an? What about, how can we guarantee that that's small, right? Sure, it converges, but what if it, you know what? How can we guarantee, I guess, that it is converging to a small value or that the terms are in itself small? Well, if you remember from previous lectures, that even though a sub n, the sequence, does depend on the choice of n, it can't be very large, right? And the reason being is because we can do that an is greater than or equal to, less than or equal to m for all n, right? Why? Because sequences, convergent sequences are bounded, right? So then this means that if we have the inequality here, this inequality, this one and this one are the same thing. Well, this is less than or equal to, well, and over here I wrote the exact same thing, but now it's with m instead of a sub n, instead of the sequence. So it's less than or equal to that because, well, our sequence is bounded, right? And now we want to make this less than epsilon. Again, here comes something a bit clever. When is this satisfied, right? So when is this satisfied? When is this, I'm going to underline it in green, when is this less than epsilon? It's less than epsilon when this bn minus b, when that distance is less than epsilon over m plus b, and an minus a is also less than epsilon over m plus b. Now, if you're wondering why this is the case, it takes some algebra to work it out, but just go ahead and plug this in for bn minus b and an minus a. And you're going to see that once you multiply them out, it's going to equal epsilon. Right, so if it's equal to epsilon, well, we don't want that, right? We want it less than epsilon, which is why we set them both less than our choice, our new choice of epsilon. Right, so now we prove it. So if you want to go back and keep that choice of epsilon in your notes, something like that, just to have it there, I'm going to put it up again here, but just to see what's happening. So if an converges to a and bn converges to b, well then an times bn converges to ab. Again, we're not just claiming it converges, we're claiming it also converges to a times b. Right, I'm going to go ahead and switch to blue. Okay, so we're going to go on with the proof. Okay, well first, as we always do, choose epsilon greater than 0. And since the sequence an is a convergent sequence, it's bounded, right? So as I mentioned last slide, we're going to set it, well, there's a positive real number m, such that all the sequences, all the terms of the sequence are less than or equal to that positive real number m for all n. Now from here, we're going to set epsilon to, well, the new case of epsilon, the one we presented in the last slide, right here. The reason we want to do that is so that our inequality is going to work, right? So if we were just to see this proof from the beginning, we would probably just say, this is too clever. They just came up with that out of nothing, magic. But no, we worked backwards, right, to see what we wanted to set our new epsilon to. So now we're going to call the new epsilon epsilon prime. So if epsilon prime is greater than 0, there's a positive integer n1, just like in the first proof, such that an converges to a. Same thing with n2 for the convergence of bn to b, right? Because we're assuming that both of those converge to their respective limit. Okay, now that we have that, we can do our work with our little inequalities. We're going to let n equal the maximum of those two. And the same is the reasoning is the same from the last proof for why that choice of n is happening. But now we work with our inequalities, or our equalities as well. So for n greater than or equal to n, this here, well, we're just going to add 0 and be clever with it, right? We're adding 0 here, just as we did last time for scratch work. Okay, well, that is less than or equal to this, which, sure, there's some work being involved here. If you missed the last slide, or if you just don't remember it, actually, we just factored out this term, the an, and we factored out b from here, and then use the triangle inequality. So we get to this bottom expression. Right now that's less than or equal to this next one. And all that changed is this an became an m. Why? It's bounded, right? So up here we had that it was bounded. M is greater than or equal to that sequence. So therefore this one is greater than or equal to the top expression. And this, we can make it small using our epsilon, right? So depending completely on this, that's less than m times epsilon prime plus b times epsilon prime, which is equal to epsilon. right? So what does that prove? That proves that an times bn converges to ab. And then here, uh, actually, well, I brought up the question, does an over bn converge to a over b? That's an interesting question. But before we even move on to that, I just want to mention some things that I'm going to write down on the side. From here, we can now see that, for example, if let's say if we had the sequence alpha times an converging, well, this actually converges to what? To alpha times a, right? Or if we had alpha as -1, sorry, I forgot to mention, alpha is a constant, right? So if alpha was equal to -1, then, or this sequence would actually converge to -a. We could even do something like alpha times an plus beta, where beta is also a constant, times bn. This would actually also, I'm going to write it down here, converge to alpha times a plus beta times b. Right, and you can play around with these. There's different properties having known that the sequences multiplied converge to ab, or that an plus bn converges to a plus b. Right, we can play around with this. But now we can move on to this question. Does an over bn converge to a over b? Well, does that even make sense? For it to even make sense, we must insist that b isn't 0 and that bn is not 0 for all n. Right, so no terms of the sequence can be 0 for this to even make sense. Okay, so just as the last slide, we're going to do scratch work. We're going to see what we want and kind of modify things to see if we can get inequalities less than epsilon to see if we can make this proof work or this theorem work. Well, we have an minus an over bn minus a over b, right? Because if it were to converge, then this is what we have here. Well, what does that equal? Well, we're just going to subtract them, right, with the same common denominator. That's equal to that. And here we're going to add 0, which we're doing here. To be a bit clever, this is less than this over here, this expression. Now, if you need the algebra practice, you can go ahead and practice that to see how we got to that expression. But because this lesson is a bit lengthy, I'm going to skip those steps. But now we need to ask ourselves, okay, well, everything over here, can we make that arbitrarily small to be less than epsilon? Well, let's take a look again. Again, an minus a, no problem, right? Why? Because they converge, and these, I can't write and talk at the same time. So an minus a and bn minus b both converge, so we can make them arbitrarily small, so they pose no problem. A over b, what is that? That is a constant, right? So again, no problem. Over here, I'm going to write for these two the reasoning. We can make them arbitrarily small. Right? Where did I get AB from? From this here. Right? So we took care of that. We took care of this. And we took care of this. But now what's left? 1 over bn, right? On both terms, actually. 1 over bn and 1 over bn. Can we guarantee that that's small? Or not that it's just small, but that it's also, that it stays away from 0? Well, bn staying away from 0, right? How can we guarantee that? If you want, you can pause it, think about it for a bit. But I'm going to write the reasoning. So, let's see. Okay, so since Bn, the sequence Bn, converges to B, excuse my bad handwriting, and B isn't 0, since it converges to B, which isn't 0, this shouldn't be difficult, right? Why? Because since B is not equal to 0, well then we can set epsilon equal to B over 2, which is obviously greater than 0. And now we have that B minus epsilon over 2, the interval, to B plus epsilon over 2 has what? It contains all but a finite number of terms of the sequence. Number of terms. So what does this tell us? This tells us that the choice of epsilon makes it clear that all terms in this neighborhood are, I should really write this. They are bounded away from 0. Right? In other words, Bn is greater than or equal to m for all but a finite number of terms of the sequence. So we're going to use this to kind of try to prove this up here. But before we do, we do need to deal with this problem first, with the 1 over b sub n. I presented the intuition, a lemma. So if Bn converges to B and B isn't 0, then there's a positive real number m and a positive integer n, such that if n is greater than big N, well then all the terms of the sequence Bn are greater than or equal to m. Right? So I'm going to put a real line to help us with our little intuition here, to help us understand. So first off, I'm going to draw B here. Actually, I should draw it somewhere. I'm going to put 0 here and B right here. Why? Because Bn converges to B and it's not 0. So I drew them apart. So we're going to set epsilon equal to B over 2. So since Bn converges to B, there's an n such that if n is greater than n, the distance between the sequence Bn minus B is less than epsilon, right? That's just convergence. We're going to let m equal same thing as epsilon, right? So we're going to use some inequalities here, or equalities as well. This here, the sequence Bn, we're adding 0. And it's greater than B minus Bn minus B, right? Using the triangle inequality. Sorry, not the triangle inequality. Something, I guess, not similar, but we're just saying here that Bn, well, here we're getting the absolute value of something, right? And over here we're subtracting 2 values. That's kind of the reasoning why this is going to be less. We're subtracting something from it. Here we're just getting the total absolute value. It's a little algebra trick. But this is greater than B, or sorry, greater than or equal to B minus B over 2. And why are we doing that? Well, here we're using that epsilon is equal to B over 2. Right? So before we move on, I kind of want to draw a picture. If we have epsilon as B over 2, that means that that's half the distance from 0 to b. So this is one that's like half the distance from 0 to b, and this is another, the other, I guess, this is a neighborhood around b, right? B minus epsilon, b plus epsilon. And we're also saying that here it's also equal to m, so m is right here. Right? And this over here, the back to the proof, well, that's just equal to b over 2. And that's equal to m, as we see here. As the picture shows us, m is right here. So all but a finite number of terms are of bn are in this neighborhood, which is greater than or equal to m. Right? So that's what this is saying. bn over here is greater than or equal to m over here. That's how we keep bn away from 0. And now this helps us with our proof now. I'm going to erase this so we can have space for our theorem. This is going to help us with our proof now. Well, if an converges to a and bn converges to b, with b not equal to 0 and bn not being 0 for all n, well, then the sequence an over bn converges to a over b. All right, and this one is probably the most involved proof, as a lot of algebra tricks are going to have to be made, or be used actually. So if you want, you can try it on your own, or just follow through and kind of verify the steps to see that you're understanding. So now we present the proof. So we're going to, just like always, choose epsilon greater than 0. Now by our lemma up above, there's a positive real number m and a positive integer n1 such that bn is greater than m for all n, or greater than or equal to n1. Then comes our little clever part that mathematicians kind of work backwards to get, is our setting epsilon, our new epsilon, equal to m times epsilon over 1 plus a over b. And again, that to understand the reasoning for this choice of epsilon, it's the same reasoning as the last slides, where you kind of work backwards with our scratch work and see what works for our new epsilon to make our inequalities or expressions less than epsilon in the end. And we're going to see it here. So here we're saying, okay, well, an converges to a. So there's an n2 such that it converges to a and it's less than epsilon. There's an n3 for sequence bn converging to b. Right, so just kind of a bit of formalities here. Notice how we have 3n. So n1 such that bn is bounded, right? It's greater than or equal to m. n2 and n3 are just showing that sequences an and bn converge to a and b respectively. Right, but now comes, well, not yet actually, we need to set n equal to the maximum. Right, and again, the maximum will suffice for all the other ones. So we're using the same reasoning over and over again for these proofs. And now comes the grunt work. an minus an over bn minus a over b. Same thing over here, just common denominator. Adding 0. There comes some algebra to show that that's less than or equal to. Actually, well, that's some algebra, triangle inequality, to show that that is less than or equal to this expression. And again, you can verify these steps using algebra. It'd be good practice. And this is less than or equal to, by a choice of epsilon, epsilon times this expression in the parentheses, And again, to verify this, you can plug in for epsilon prime, what we have up here, to see why that is indeed less than this expression up here. But again, because of the length of this lesson, I'm going to skip that. Just algebra you can do on your own. And that is less than or equal to epsilon prime times 1 over m, and then times, in parentheses, 1 plus a over b. And that is equal to epsilon. So mathematicians kind of started here with this epsilon and worked backwards to see what they needed to prove this. Right, so what did we just show? That this over here is less than epsilon, which shows that, well, an over bn, the sequence, converges to a over b. So this is probably the most involved proof of this lesson, but we're not quite done yet. So next up, I have a question. We're going to suppose an and bn are sequences converging to a and b respectively. Does an over less than bn for all n? So all the terms in an are less than bn for all n. Point-wise, that is. Does that imply that the limit it approaches or it converges to is less than the limit of b, of bn? We'll try to think about how to prove that, or maybe if it's not true, how to give a counterexample. So go ahead and pause the video and think about it for a little, and we'll go over it shortly. Okay, if you came up with a counterexample, congratulations. We're going to present one now. This is a bit unintuitive because I'll admit the first time I saw it, I did think this would hold. But the counterexample can be that we consider sequences 1 over 2n squared and 1 over n. And the first sequence is less than the second sequence for all n, but they both converge to 0. So a is not necessarily less than b, unfortunately. But we can present something. We're going to present such a thing such that if an is less than or equal to bn for all terms, well then a is greater than or less than or equal to b. So it's not a strong inequality, but it's still less than or equal to. Right, and I have the real line up here just in case we need it for our proof or our theorem. But the way this is going to work is going to be by contradiction. We're going to show that a greater than b leads to a contradiction. And hopefully this real line helps with the understanding of this proof. But we're going to present the theorem. If an converges to a and bn converges to b, with an less than or equal to bn for all n, then the limit point a is less than or equal to b. Okay, so I'm going to start off with saying that where our assumptions, right? So suppose an converges to a and bn converges to b. And here we have that b is less than a. Right, so an is less than or equal to bn for all n, and b is less than a. So here we're assuming b is less than a, so on the real line, I'm just going to draw b on the left, a on the right. Well, then we're going to set epsilon equal to a minus b over 2. Right, and as we saw, that's equivalent, so that half the distance, right? So that's our epsilon neighborhood around both limit points. And if this helps, you can kind of already see how the contradiction is going to work. Right, because all the terms in an, all but a finite should be in this neighborhood over here, and all but finite should be, for bn, should be in this neighborhood over here. So we're going to see how this works. First off, just as I said, there's a positive integer n1, such that all the terms, and an, I'm going to put over here, an is in green, and bn is in blue. So after positive integer n1, all the terms of an are in this neighborhood. Just a bunch. All but a finite after that n1. After the n2, all but a finite are in here. Right, and I'm just drawing a bunch, but there are infinitely many points in this neighborhood and infinitely many points in this other neighborhood of their respective sequences. So we're going to choose n to be the max again, because the maximum suffices for both of them. So we have this inequality here. Bn is less than b plus epsilon, right? All the terms are less than this here, this. All the terms of the sequence, except for finite, are below that, so are this way. And well, this is also equal to a minus epsilon here, which is less than or equal to all but a finite terms of an in this neighborhood. Well, why am I using blue? That's confusing. Sorry, I messed these colors up. I was using bn, green for bn, so I should use okay, so just quickly, bn down here in the proof, bn is less than or equal to its, I guess, upper interval, upper, I guess, bound of the interval. Right, so that all these points are less than or equal to this right here, this parentheses, and that parentheses is the same parentheses as this one that we have over here, which is a minus epsilon, and that is less than infinitely many an terms. And here, by hypothesis, we said that an is less than or equal to bn for all n, so that's how we get this. But wait a minute, we just said bn is less than bn? Well, that's where the impossibility comes in. This inequality is impossible, which is a contradiction, and we get our theorem proved. Okay, last slide. Another interesting thing about sequences is we're going to consider this sequence. And I'm not going to say because you can see it. It's a bit lengthy to say. So this can be viewed as a product of two sequences, which are the other two right here. So now, just as a reminder, this is sine n pi over n, I guess y is equal to over, oh, what? I wrote, there should be n pi over 2, sorry. That's how that looks. And then just recall, remember when we were proving that an times bn minus ab, how that was less than or equal to this expression over here? Remember how we were trying to get each of these, I guess, terms or little expressions, an minus a, b, bn minus b and an to get arbitrarily small so it can be less than epsilon. That's where we were. And the reason we're going to recall this is because we're going to use it to prove something. But what happens if we let an, in this case, be the sequence sine n pi over 2 and bn be 1 over n? Well, in this case, even though sine, this function up here, or this sequence, actually, yeah, this function here, well, it doesn't converge, right? It doesn't converge to any number. If we were to draw the points of the sequence, doesn't converge. But what do we notice? That it is bounded, right? So what does this mean? First of all, well, if bn, we know this converges, this sequence converges to 0, right? So b here is 0. So this, no matter what it is, it's going to get multiplied by 0. So this here is going to become 0. Now what about the other part? Well, the sequence an, this sequence is bounded. Right, as we can see up here, this is bounded, an. And we can make this other thing, bn minus b, arbitrarily small. Right, so something that's bounded times something that we can make arbitrarily small will eventually, well, I guess using that word loosely, get to 0. Right, it'll be less than epsilon, definitely. So what can we prove now? This theorem that if an converges to 0, in this case, an, we switched it up here. Here we had this converges to 0, and bn is bounded. I guess for this theorem to not be confusing, there should have been bn and there should have been an. But in general, without even looking at the example above, we have the theorem that if an converges to 0, if we have a sequence that converges to 0 and the other sequence is bounded, I should have wrote it like that, then their product converges to 0. Right, so we're going to just prove this, and it'll be our last proof and our last thing for this lecture. So proof, we're going to let m be a positive integer such that all the terms of bn are bounded, right, because we're assuming bn is bounded for all n. And then we're going to choose epsilon to be greater than 0. I want to set this new epsilon equal to epsilon over m. And the reason for this choice of epsilon, of this new epsilon, will be apparent shortly. But you should have probably have already anticipated this choice if you've been practicing these in your class. So there's a positive integer n, right, such that an minus 0, since it converges to 0, is less than epsilon prime. And now we're going to use our equalities and inequalities to show that an times bn converges to 0, right? Well, that's just equal to an times bn. That is equal to an times bn in absolute values. Again, here a lot of students make the mistake of writing less than or equal to. And it's actually just equal to, right? We're not adding. We don't have any addition, so it's actually just equal to. And that is now less than an, less than or equal to, sorry, an times m. Why? Because, well, bn is bounded by m. The sequence bn is bounded by m. And now, here comes for the choice of epsilon, the reasoning is because now that's less than our new epsilon times m. which is equal to epsilon. Right, so we just showed that the product of these two sequences is less than epsilon and therefore converges to 0. So a lot of theorems and proofs in this section use pretty much the same reasoning, actually. Pretty much all of them use the same reasoning. So if you need to work out some details, maybe try them on your own. That would be really useful. So you can kind of internalize these ideas, these reasonings. I know for the sequence an over bn converging to a over b, that one was a bit involved, quite complicated. If you can get that one, you can pretty much get anything in this section. And if you were able to follow through, you should be good. And for the next sequence, we're just going to be, for the next lecture, we're going to be looking at sequences, but something called subsequences, which is a sequence you get from a sequence.